Okay, so we continue to do question 8.3. Question 8.3 is basically a game. So the name is the game of chicken. So where we basically have two players moving towards each other, and they will have an option to either veer away or not to veer. Okay, so basically both of them choosing not to veer. So basically, if they are choosing to go towards each other, they will have a crash, and the payoff for them gonna be worse. So the case is where we have player 2 and player 1 here. Each of them will have an option to either veer away or do not veer. So same for player 1 to veer away or not. Okay, so the payoff corresponding to each of this strategy is if both of them choose to veer away, each of them will get 2 and 2. If one of them chooses to veer and the other one chooses not to veer, they will get 1 and 3. So the person who chooses to veer will basically get these from other friends, basically become a coward. So ever so just get a pair of 1. The person who choose not to veer will become like a hero and will get 3. So similar, if this one so player 1 choose not to veer, he will get 3, and player 2 choose to veer, he will get 1. And if both of them choose not to veer, they will be hitting each other, and each of them will get 0 and 0. Okay, so they will be in a crash. So part A of the question asking you to draw an extensive form of the game. So again, extensive form is the game tree where one of the players moving first, and the second player, after observing the action chosen by the first player, will be choosing their action accordingly. So I'll say player 1. So assume player 1 is moving first by choosing either veer or not veer. And then player 2, after observing the action chosen by player 1, he will be choosing the action that will give him a best payoff. Okay, so player 2 here, so he can choose either to veer or not. Or not. Okay, and corresponding to each of that, there will be a payoff here. So if player 1 choose to veer, player 2 choose to veer as well. Each of them will get 2 and 2. This will player 1 2 to veer, player 2 choose not to veer. He will get 1 and 3, 3 and 1, and then 0 and 0. Okay, so that's the extensive form of the game. Part B, find a pure strategy Nash equilibrium or equilibria. Okay, so in order to find a pure Nash strategy equilibrium, we just have to use the table over here. So this is the case where both of the players are moving simultaneously. So again, in order to find a pure Nash strategy, Nash equilibrium, you will just have to consider the optimal strategy for each of the player, given the strategy chosen by the other player, and the Nash equilibrium gonna be the optimal strategy for both of the player given the strategy chosen by the other one. Okay, so at the equilibrium, none of the players will have incentive to deviate from the strategy they already chosen. Right, so in this case, we say if player 1 choosing to be the optimal strategy for player 2 is to choose not to veer, because he will get 3 instead of getting 2 in this case. So I'll put a star here. If player 1 choose not to veer, the optimal strategy for player 2 will be choosing to veer, because I will give him 1 instead of giving him 0. So I'll put a star there. So we come to player 2. So the best strategy for player 2, I'm sorry, if the player 2 is choosing veer, what is the optimal strategy for player 1? Okay, so player 1 will be choosing not to veer, because that will give him 3 instead of getting 2 by doing veer. So I'll put another star here. And if player 2 decide not to veer, the best strategy for player 1 will be to veer, because that will give him 1 instead of getting 0 in the crash. And I put a star here. Okay, so as I said before, the cell that including 2 stars will be the equilibrium, will be the pure Nash equilibrium. So in this case, this is going to be the equilibrium, and this is going to be another equilibrium. Okay, so we have 2 equilibria, which are the pure Nash equilibria. Okay, so the pure Nash equilibria are not to veer by the first player, and then veer by the second player, and veer by the second player, and not to veer by the veer by the first player, and not to veer by the second player. Okay, so we have 2 Nash equilibria. Part C, compute a mixed strategy Nash equilibrium. And then it's asking us to draw the best response function for each player on a graph. Okay, so again, we just do the mixed strategy equilibrium. So again, we just have player 2 here, player 1 here. This one can choose to veer or not to veer. This one can choose veer or not to veer. And in each of them, they will have a payoff 2, 2, 1 and 3, 3 and 1, and 0 and 0. Okay, so again, I let alpha be the probability that player 1 will be choosing to veer, and 1 minus alpha therefore will be the probability that player 1 choosing not to veer. Beta will be the probability that player 2 is choosing to veer, and therefore 1 minus beta is the probability of not veering. Okay, so we will just have to find the values of alpha and beta in order for both of the player to be indifferent between choosing veer and not to veer, so that they will be randomizing on both of the actions. Yep, otherwise they will just choose a pure strategy. Okay, so in order for them to choose a mixed strategy, we just have to make the payoff equal to each other, just like what we did before. Okay, so we do for the player 1 first. So the payoff, the expected payoff that player 1 can get by choosing to veer. So if he choosing to veer, depending on the strategy chosen by player 2, he will get a certain payoff. Okay, so better of the chance player 2 will be choosing to veer as well, and he will get 2. And 1 minus beta of the chance player 2 will be choosing not to veer, and player 1 will get 1 by choosing to veer, and the expected payoff will be beta plus 1. Okay, so the payoff, the expected payoff, so I'll say expected. Okay, so the expected payoff for player 1 by choosing not to veer is gonna be so again, beta probability that player 2 gonna be choosing to veer, and if player 1 choosing not to veer, he will get 3, and 1 minus beta where player 2 choosing not to veer, and player 1 if choosing not to veer as well, both of them going to be in a crash, and he will get 0. So the expected payoff therefore will be 3 beta. Okay, so in order for P1 to be okay, so now if the expected payoff, okay, so I'll say the expected payoff of choosing veer is smaller than the expected payoff choosing not to veer for player 1. So player 1, that basically means beta plus 1 is smaller than 3 beta, and so therefore it will be 2 beta is bigger than 1, and therefore beta is bigger than a half. Okay, so if this is the case, then that basically means the expected payoff of not veering will be higher than expected payoff of veering. So the optimal strategy for player 1 is to choose not to veer. Okay, so choose not to veer, so that basically means corresponding to alpha equal to 0. Okay, so you can see from here, if alpha equal to 0, the probability of veering is 0, so he will be playing a pure strategy of not to veer. Okay. Now opposite case where the expected payoff of veering is bigger than the expected payoff of not to veer for player 1, and therefore beta will be smaller than a half, and the strategy in this case will be to veer, okay, because the expected of veering is higher. And that's in the case where alpha equal to 1. Okay, so we don't have any mixed strategy. This is the pure strategy where they are 100% sure that player 1 will be choosing to veer because the expected payoff of doing so is bigger than the expected payoff of not veering. And if they are equal to each other, which basically mean when beta equal to a half, then the player 1 will be indifferent between veering, so will be indifferent between veer and not to veer, and therefore alpha can be anything between 0 and 1. Okay, so it doesn't really matter, so either alpha equal to 0, alpha equal to 1, alpha anything between, that will give the player 1 the same expected payoff because the expected payoff of choosing to veer and not to veer are just equal to each other. Okay, so that is where the mixed strategy comes in, when the player 1 is not different between two of the strategies, so he will be randomizing on both of the actions. Okay, so it's similar for P2. Now the expected payoff for player 2 by choosing to veer will be equal to, so if player 2 choosing to veer, depending on the strategy chosen by player 1, that will determine the payoff that player 2 will get. So it will just beta, so alpha probability that player 1 will be choosing to veer and player 2 will get 2, 1 minus alpha percent that player 1 choosing not to veer, and player 2 will get 1 by choosing to veer. Okay, so the expected payoff will be alpha plus 1, and expected payoff for player 2 by choosing not to veer will be alpha multiplied by 3 plus 1 minus alpha multiplied by 0, and that will just equal to 3 alpha. Okay, so similar idea. If expected payoff for player 2, if he choosing to veer is smaller than expected payoff if he choosing not to veer, that's the case where alpha plus 1 is smaller than 3 alpha, which is basically mean alpha is bigger than a half. Then player 2 will be choosing not to veer because the payoff is higher, and that is where beta equal to 0. Okay, so if player 2 choosing not to veer, he will be playing the not to veer strategy with 100%, so that basically means beta equal to 0. Okay, so opposite case where veer is bigger than expected payoff of not to veer. That's in the case where alpha is smaller than a half, then the best strategy for player 2 is choose to veer because the payoff is higher, and this is the case where beta equal to 1. Okay, that basically means he 100% show that he will be choosing to veer, so beta equal to 1, and that is the pure strategy. Okay, if the payoff are equal to each other, therefore alpha equal to a half, then he will be indifferent between veering and not. So therefore beta can be anything between 0 and 1. Okay, so this is the mixed strategy. Okay, where the player 2 is randomized on both of the action because he is indifferent between both of them. Again, this is also the mixed strategy. Okay, so the mixed strategy Nash equilibrium will be So that would be player 1 choosing between veer or not to veer with alpha equal to a half, and for player 2 is veer and not to veer with beta equal to a half. Okay, so that is a mixed strategy Nash equilibrium. Actually, the player will be playing a mixed strategy with half of the probability that they will be playing veer and half of the probability, and the probability of half they will be playing not to veer. Okay, so we're gonna be drawing a bet response function for action player on the graph. Okay, so we'll be having something like this. So outside on the vertical, I got player 2. So the probability that player 2 is choosing to veer. Probability, so that basically beta. And on horizontal, I will have player 1 veer probability. So that will basically alpha. Okay, and I got 0 from here. Right, so just like what we found before, the mixed strategy happened when alpha equal to a half and beta equal to a half. So I know that I got half and half there. Okay, so we consider for player 1 first. Now, as we said before, for player 1, for any beta smaller than a half, so here's player 1, yeah. So for any beta smaller than a half, he will be choosing to veer. For any beta bigger than a half, he will be choosing not to veer. Okay, so for beta smaller than a half, he will choose alpha equal to 1. That basically means he is 100% choosing to veer. So alpha will be equal to 1. And with beta bigger than a half, alpha will be equal to 0. Beta equal to a half, alpha can be anything in between because the player is indifferent. So having said that, for any beta smaller than a half, so 0 here, half here, remember the beta is on the vertical. So for anything from 0 to a half, player 1 will be choosing alpha equal to 1. Okay, so I got alpha equal to 1 here, alpha equal to 1 here. So for anything from 0 to a half, alpha will be equal to 1. So I will just have a vertical line going up from 0 to a half. See this one. Okay, so for anything from 0 to a half, alpha will be equal to 1. For anything from a half to 1, so for any beta bigger than a half and smaller than 1, remember beta will have to be in between 0 and 1, so it has to be smaller than 1. For any beta is bigger than a half, smaller than 1, alpha will be equal to 0. So I know that alpha equal to 0 is here. So that basically means I got to this one. That's the line. Okay, so for any beta bigger than a half, my alpha will be equal to 0. And for beta equal to a half, alpha can be anything in between. So this is alpha 0, this is alpha equal to 1. Any alpha in between means anything between 0 here and 1 here will be okay. So that basically the horizontal line like this. Okay, so for beta equal to a half, this is where beta equal to a half, alpha can be anything in between. So I draw a horizontal line indicating that alpha can be anything in between 0 and 1. Okay, so my black line here is the best response function for player 1. Okay, so I'll use a different color to draw for player 2. So I'll use a red one. Okay, so similar for player 2. So we already found out for player 2. For anything for alpha smaller than a half, he will be choosing to veer. Okay, so alpha is on a horizontal. For any alpha smaller than a half, so from 0 to a half, player 2 will be choosing to veer. So that basically means he will be choosing to play beta equal to 1. So he will be 100% choosing to veer, so beta will have to be equal to 1, and that is a pure strategy. Okay, so beta on a vertical, beta equal to 1, which is this one, and for anything from 0 to half, for any alpha from 0 to a half, beta will have to be equal to 1. So that's why I draw a horizontal line from 0 to a half, and at the point where beta equal to 1. Okay, now for any beta, so for any alpha is bigger than a half, beta will be choosing to not to veer, and that's the case where where beta equal to 0. So for any alpha bigger than a half, beta will be equal to 0. So beta will be equal to 0 at this point here. For any alpha bigger than a half, which is this one, to 1. So for any alpha bigger than a half until 1, beta will be equal to 0. So that's basically a horizontal line. Okay, and for alpha equal to a half, beta can be anything between 0 and 1. So beta equal to 1 here, beta equal to 0 there, beta equal to 1 here, anything in between, basically anything on the vertical line. So I will just draw a vertical line saying that at the point where alpha equal to a half, beta can be anything in between. Okay, so we can have any point here, here. So beta can be any point, and that will just give the player 2 the same expected payoff. Okay, so the red one is the best response function for player 2. Okay, so as you can see from here, the intersection here is the mixed strategy equilibrium, where each of the player is playing a mixed strategy with a probability equal to a half. Okay, so they will be randomized on both the action with a probability equal to a half. Okay, so this is the mixed strategy Nash. Okay, as you can see, there is another intersection here, and there is another intersection there. So that basically the pure strategy where the player choosing to play the probability beta equal to 1, and here is alpha equal to 1. So that basically is a pure strategy, not the mixed strategy Nash equilibrium. Okay, so only the intersection here is the mixed strategy Nash equilibrium. Okay, so D. Suppose the game is played sequentially with player 1 moving first. Okay. So question asking you to find the contingent strategy for player 2. Okay, so player 1 is moving first. So write down the normal and extensive form of the game, of a sequential game. Okay, so I'll just draw an extensive form first because that's easier. Okay, so I have player 1 is moving first. So player 1 can choose to veer or not. And then player 2 will be observing the action chosen by player 1, and then will decide the action. They're going to be giving him the optimal payoff. So he can choose to veer or not to veer. Choose to veer or not to veer. Okay, and then each of the action here will have a payoff. Again, 2 and 2, 1 and 3, 3 and 1, and 0 and 0. Okay, so we already have the extensive form before in part A. Now the normal form of the game. Okay, so the normal form is the table form. Now remember, it's not a table that were given to you at the beginning of the question. Now the normal form of the sequential game. Okay, so you have to take into account that player 1 is moving first, and player 2 will be observing the action chosen by player 1, and he will be deciding the action that he should be choosing afterwards. Okay, so remember player 1 is moving first, so I got player 1 here, again I got player 2 here. Player 1 still have two options, either veer or not to veer. Now the thing different here is player 2 will be having a 4 different strategy, okay? Because player 2 will have to observe the action chosen by player 1 and then determine the action chosen by him. Determine the action he's gonna be choosing. So player 2 will have an option of choosing exactly the same strategy as player 1, or choosing to veer all the time, or choosing not to veer all the time, and choosing the opposite action to player 1. Okay, so having said that, I'll say player 2 will have an option of choosing V and V. So what does that mean by having V and V here? So that basically means, so the first one indicate that this is the action player 2 will be choosing in the case player 1 choosing to veer. Okay, so remember player 1 have two actions, either veer or not to veer, and this is the strategy chosen by player 2 given each of the strategy chosen by player 1. Okay, so if player 1 choosing to veer, player 2 will be choosing to veer. If player 1 choosing not to veer, player 2 will still choose to veer. Okay, so that the meaning of V and V here. That basically means player 2 choosing to veer no matter what. Okay, doesn't matter what action player 1 is choosing, I will choose veer all the time anyway. So player 2 will have another action of VN. So that basically veer and not to veer. And veer and not to veer here mean if player 1 choosing to veer, I will choose to veer. If player 1 choosing not to veer, I will choose not to veer. Okay, so this is the action by player 2 given the first action by player 1. This is the action chosen by player 2 given the second action that chosen by player 1. Okay, so again player 2 will have another option of not to veer and veer. So that basically means if player 1 choosing to veer, I will choose not to veer. If he choosing not to veer, I will choose to veer. So I'll choose to do the opposite to what he did. And the fourth action, the fourth strategy for me is no and no. So basically mean I will choose not to veer no matter what. So if he choosing to veer, I will choose not. If he choosing not to veer, I will choose not anyway. Okay, so player 2 will be choosing not to veer. Doesn't matter what action is chosen by player 1. So those are the strategy that player 2 will have to face, and corresponding to each of those, there will be a payoff. Okay, so if player 1 choosing to veer, player 2 choose V and V. That basically means if player 1 choose to veer, I will veer. If player 1 choose to not veer, I will veer anyway. Okay, so in this case, if player 1 choosing to veer, I will choose to veer, and that will give me a payoff of 2 and 2. This is the case where player 1 choosing to veer, and according to my strategy here, I will choose to veer. So again, I get 2 and 2. This is where player 1 choosing to veer, and my strategy is I will choose not to veer. Okay, so consider the first one here, which is the strategy by player 2, given the strategy chosen by player 1. So player 1 choose to veer, I will choose not to veer, and in that case, the payoff will be 1 and 3. Similar here, if player 1 choose to veer, I will choose not to veer, and we both get 1 and 3. We again get 1 and 3. Okay, so this is the case where player 1 choose not to veer. My strategy is I will choose veer anyway, so doesn't matter. So if player 1 choose not to veer, I'll choose to veer. The payoff will be 3 and 1. This is the case where I do opposite to what, I'll do exactly the same as what player 1 doing. So if player 1 choose not to veer, I will also choose not to veer. And if that's the case, each of us will get 0 and 0. So this is the case where player 1 choosing not to veer, I will choose to do the opposite. So if he choosing not to veer, I will choose to do veer. Okay, the second letter here, and that will give me an option of 3 and 1. And This is the case where I choose not to veer no matter what. So if player 1 choose not to veer, I will also choose not to veer. Each of us will get 0. Okay, so that is how you do the normal form for a sequential game. It's a bit more complicated, but just a bit be careful with that. Okay, A. So using the normal form of the sequential version of the game, solve for the Nash equilibrium. Okay, so we have a normal form here. We just have to solve for the equilibrium. Very straightforward. Again, just have to consider the best strategy for each of the player given the strategy chosen by the other player. So if player 1 choosing V, best strategy for player 2 is this, because that will give player 2 a payoff of 3 instead of payoff of 2 in the first two cases. Okay, if player 1 choosing not to veer, best strategy for player 2 is choose choose to veer, and here and here is the best strategy, because that will give the player 2 a payoff of 1 instead of getting 0 in this case here and this case here. Okay, now consider the best strategy for player 2. If player 2 choose VV, best strategy for player 1 is N. Player 2 choose VN. Best strategy for player 1 is V. Best strategy for player 1 is N. Best strategy for player 1 in this case is V. Okay, so any cell that includes 2 stars, that will be the equilibrium. So we got this one, and this one. Okay, so basically we have 3 Nash equilibria. So that will be veer, not, veer, and not veer. Okay, so those are the Nash equilibrium. F. So using the proper subgame using the extensive form of the sequential game, using the backward induction to solve for the subgame perfect equilibrium. Okay, so we want to find the subgame perfect Nash equilibrium. Subgame perfect equilibrium. Okay, so we use the extensive form of the game here. How do we use the backward induction to solve for the subgame perfect Nash equilibrium? Okay, so basically, how many subgame do we have here? So subgame basically the small game that played by each player. So first of all, you can see we have one subgame here, which is the first. Okay, so this is the first subgame. This is the second subgame, and this is the third subgame. Okay, so basically, this is the subgame played by player 2, this is the subgame played by player 2, and this is the subgame played by player 1. So basically, this is the whole game itself. So we will be solving for the equilibrium in each of the subgame, and then we solve backwards to find the equilibrium in the bigger game here. Okay, so say what is the best strategy for player 2 in this subgame small game here? If player 2 choosing to veer, he will get 2. If choosing not to veer, he'll get 3. So best strategy is this one, not to veer. Okay. For the second subgame, player 2 choosing to veer, he will get 1. Choosing not to veer, he will get 0. So the best strategy is choosing to veer. So that's the equilibrium in the second subgame. So we're done in the second stage. We will be moving backward to find the first stage equilibrium. So say player 1 can choose either to veer or not to veer. And knowing that if player 1 choosing to veer, player 2 will be choosing not to veer in the second subgame, and he will get 1. Okay. Now if player 1 choosing not to veer, he knows that player 2 will be choosing to veer, because choosing to veer is the optimal strategy for player 2 in that subgame, and he will get 3. Okay, so the optimal strategy for player 1 is choosing not to veer, because he will get 3 at the end, which is bigger than 1. So we have solved for all of the equilibrium in each of the subgame. So the Nash equilibrium will be, the subgame perfect equilibrium will be player 1 choosing not to veer, and player 2 observing that action, he will be choosing to veer, and each of them will get 3 and 1 respectively. Okay, so subgame equilibrium is choosing not to veer by player 1 and choosing to veer by player 2. So explain why the other Nash equilibria of the sequential game are not reasonable. Okay, so we found 3 Nash equilibria here by using the normal form of the game, and we only found one subgame perfect equilibrium here. So what are the other two that not really reasonable? So as compared to the extensive form of the game, as you can see, the strategy NN, that basically not to veer no matter what, is not reasonable, because if you're looking back at this the extensive form of the game, if player 1 choosing to veer, okay, optimal strategy for player 2 is choosing not to veer. But if player 1 choosing not to veer, optimal strategy for player 2 should be to veer. Okay, so basically not is not reasonable, because it's not the optimal strategy for player 2 to play. Okay, so that is the reason why VNN is not reasonable, because N and N is not optimal. Okay, so optimal is where player 2 is doing opposite to whatever player 1 did. So if player 1 choosing to veer, best strategy for player 2 is choose not to veer. If player 1 choosing not to veer, the optimal strategy for player 2 is choose to veer, according to the extensive form of the game. Okay, by solving the subgame equilibrium, we found that. So we know that N and N is not reasonable. Now V and V. So another Nash equilibrium is NVV. This one is not reasonable either, because V and V is not optimal. Okay, by choosing veer no matter what, is not the optimal strategy for player 2. As I said before, optimal strategy for player 2 is to play opposite to whatever player 1 did. So by playing V and V, no matter what player 1 did, is not optimal. So that's the reason why this Nash equilibrium is not reasonable either. So we only left with the last one, which is this one. So only N and NB is the optimal strategy, where in the equilibrium, where player 2 will be choosing opposite to what player 1 did, and that will come back to the subgame perfect equilibrium. Okay, so basically we say this is the credible equilibrium, and the other Nash equilibria are not reasonable, are not credible.